Hi, everybody. Good to see you again, or at least sense your presence. Okay, who's ready for a new session of exciting talks? I know you're already halfway through, so you don't have to answer that.
Yeah, so you want to go ahead and share the slide?
Yeah.
Okay, so this afternoon, we're going to be covering the Rocprof-compute tool, plus a few other profilers, some new profilers that are just coming out with the ROCm 7.0 release, and then a system administration presentation. So we've got a fair amount of material to cover today, this afternoon. So Giacomo, you want to go ahead and start?
Okay, yeah. So you may have seen this slide already today, though with a different rectangle that was highlighted in pink here. So now it's time to turn on the Rocprof-compute rectangle and discuss this. So Rocprof-compute is the kernel performance analysis, and it's the tool that you would use basically at the end of your profiling journey after you have found what kernels are the ones that are worth optimizing and perfecting, basically. And Rocprof-compute uses Rocprof v3 behind the scenes, which itself relies on Rocprofiler SDK. So Rocprof-compute has been introduced starting from ROCm 6.3. Actually, that has just been renamed because the tool that used to exist before it was renamed was actually called OmniPerf. So contrary to Rocprof-sys, for instance, that exists separately from OmniTrace, Rocprof-compute is actually just a renaming of OmniPerf. So you won't find a separate OmniPerf branch on GitHub as you can for OmniTrace. So the most notable features for Rocprof-compute are that they can provide rooflines to quantify the performance of your GPU kernels based on the achievable hardware limits. Something else that's very interesting is you can do kernel comparisons. So you can basically compare two different implementations of your kernel head to head and actually see what changed in performance. You can get a lot of performance metrics, and then you also have support for speed of light and memory chart. Okay, so starting from the beginning, we should briefly talk about what a roofline is. So basically, a roofline is this graph here that is intended to locate your kernel on this 2D plane so that you have an idea of how well or how bad your kernel is performing. So on the x-axis, you have the arithmetic intensity that's defined here. So it's peak flops per second divided by bytes per second. And on the y-axis, you have the attainable flops. And the two lines that you have to pay the most attention to here are the line that's the bandwidth bound and the line that's the compute bound. So see, basically, the attainable flops are the region in this plane that lives below those lines. So this one is the bandwidth bound, and the horizontal one is the compute bound. So your kernel, your data point for your kernel will live somewhere below these two lines, which are the roof lines, basically. And then anything that's above that, it's not attainable. So see that This bandwidth bound here is basically defined as a line. So it's through the origin. So that's just y equals m times x. And the m is your HBM bandwidth. So the m is what basically decides the slope of the line, and that's your HBM bandwidth, or the bandwidth in general. So here we're talking about HBM, but we'll see also L1 and L2. So the slope is the bandwidth. And so basically, if your kernel sits close to the bandwidth bound line, then it's bandwidth bound. If it sits close to the compute bound, then it's compute bound. And if it's below any of those bounds, then the performance can be improved. So here we've talked about the ghost exchange example yesterday. So here we are basically showing you an actual roofline that's been obtained with Rocprof-compute. And it's providing data not just for the HBM, but also for the L1 and L2 cache and LDS. You see that those have a higher bandwidth than the HBM, so those lines are above. And you see that our blur kernel, which is the one that was doing the averaging of the solution, sits very close to the bandwidth limit. So that is most certainly bandwidth bound. And this is with the HIP implementation of the ghost exchange. And the init core is just one kernel that was initialized in the solution. So the performance is pretty bad there, but it's called only once, so it shouldn't be too big of a deal. So in terms of getting more out of Rocprof-compute after you've gotten the roofline, you can use Rocprof-compute profile with the -- no roof option so that you don't waste time generating the roofline, because for that you have to run the application several times. And this will give you some data that you see you're calling V1 here. So in the case you're running on 300A, your data will be saved in this directory workloads V1, and then if it's 300A, MI300A. And then after you have run the Rocprof-compute profile, you can analyze the data that you've got with Rocprof-compute analyze. And if you do the -- list stats, you'll get something like this that will show you the IDs of each of the kernels that you have in your application. You can also list the dispatches. So the dispatches are basically the IDs of the kernel, considering the order in which they have been launched. So if you do that and grab on blur, then you can see which dispatch ID the blur kernel has been associated with. The thing that I was telling you before, the comparison of two implementations is also done with Rocprof-compute analyze. So say that you decide to change the launch parameters of your grid. So you're gonna be running Rocprof-compute profile once again. Just call it something else here. We're just calling it V2. And then you are going to run Rocprof-compute analyze with the -p for the first workload and -p for the second one. And basically you'll get a plot like this one that's comparing the first one as baseline with the second one. So basically the average, the first column that says average refers to the first one, the second one to the second one, and then you've got the difference. So yeah, so now there's gonna be a few exercises that I'll walk you through that are intended to basically show how you can use Rocprof-compute to spot problems and fix them. So the thing with these examples is that obviously we constructed them, so in a way we already knew where to look, and I think that probably the hardest part is actually, that like knowing how to sort out the output that you get and be able to identify what's meaningful and what's not. So that's unfortunately the hardest part. But here we assume that we already know that, and so we'll make that a little easier for the rest of the presentation. Okay, so we're gonna go over the examples in our training examples repo under the directory Rocprof-compute. These results have been obtained with ROCm 640, but if you log in to AAC6, we have Rocprof-compute 641. So you can test that one. And just a warning here, these are kernels that are not fully optimized. They're just used to kind of showcase some of the features of Rocprof-compute and how it can help you with your own workloads. Okay, so let's go ahead and dive into the first one. So throughout the examples that I'll show you, we're considering a kernel that's doing a vector matrix vector product. So it's YAX. And A is this array that's been basically unrolled into one D array like that. And we want to optimize a kernel that looks like this using HIP. But the thing about this presentation is that we picked HIP, but we're not going to be talking too much about HIP, and the most important concepts and takeaways don't really depend on HIP. Okay, so the first thing we do is we generate a roofline. So notice that we're using Rocprof-compute profile. We're giving some name to the data that we get. We'll run with dash roof only, so we only do the roofline. And then we specify the dash kernel dash names so that we get a separate file that tells us what point in the roofline corresponds to what kernel. Yeah, so we see that for this YAX kernel, initially we have pretty poor performance. So in the initial situation is a situation where we're not having good occupancy. We're just using only a few number of threads. So the change that we're gonna be making is we're gonna increase the occupancy basically. And note here that sometimes the data points are actually one on top of the other, so it may look like they're not there, but if you're able to zoom in, then you're gonna be able to see them. So, so yeah, see here that the change that we're gonna make here, problem is basically the one we start from, and a solution is what we modify. So we modify the launch parameters to have more occupancy. So we have basically more blocks in our grid, and each block is made of 64 threads, which is the wavefront size. And this is with HIP. So here we're making this comment that sometimes launch parameters can be obfuscated by OpenMP. Yes, although you now know that you can interfere with that. You can specify, for instance, the number of threads, and that will be the block size, or the number of teams, and that will be the grid size. And you can also set libomp target kernel trace to 1. And with the latest compilers, that will also tell you not only the launch parameters, but also the occupancy. So there are ways to get that information from OpenMP as well. So yeah, so what we see, once again, we're doing the Rocprof-compute analyze. So we're comparing these two workloads. The gray one is the baseline, what we call problem. and the blue one is the solution. And we see that just with this simple change, we've gotten a 56.6x speed up. So we increased the occupancy. We used more threads basically, and that helped a lot. So see that the points have moved up. Notice that the roof line on the right has a changed scale on the y-axis. So see here on the left, the 100 is here, and on the right is here. So those points actually moved up quite a bit. Yeah, so this was a simple case. And notice how we are filtering what we are looking at, because you'll see that the output that you get is a lot, maybe a little overwhelming at first, but we think that it's better to have more than less at times, and that it just takes a little bit of experience familiarizing with which specific blocks are most relevant to what you need. So for instance, you see here, this number here at the top left is the block 7.1 for the wavefront launch stats. So here, when you launch the Rocprof-compute analyze and filter the blocks, if you do 7.1.0, 1.1, and 1.2, you'll get those ones associated with the launch parameters. For this second example, basically, we are exploring the effect of allocating local data store memory for our kernel. So initially, the problem, so the reference solution is the one where we are basically allocating all the LDS that we can. So see, this fully allocate LDS is computed so that that's the maximum number of doubles that you can fit into 64 kilobytes of memory. And the solutions are either you don't use LDS or you just reduce the size, because if you use too much, then you restrict the occupancy, because LDS, as you know from one of our previous talks, is shared among the wavefronts. Yeah, so what we have now is that by comparing the fully allocated LDS with a reduced allocation, then we get a little speed up. But the important thing here is that we are looking at well, yes, the wavefront occupancy, but also quantities and markers such as the insufficient CU LDS. So that is defined as the percent of total compute unit cycles in the kernel where work group could not be scheduled due to lack of available LDS. So if that goes down, then that's good. Okay, so the other example that we wanted to kind of look into is how to diagnose a register occupancy limit. So in the code that I'm not showing here, there's basically an assert to check that something is 0. And it's also at times kind of surprising how just a simple function call can create rather big issues in terms of performance. So the solution just removes that assert and compares the performance. And I'm not gonna describe the registers here since we actually talked about them already in the HEAP presentation. So yeah, so there's just a little improvement here. It is not dramatic, but in general, this was not necessarily the case, but there are other cases where, for instance, calling math functions heavily inside the kernel can clog your register use a little bit. Okay, yeah, and also notice that we are filtering with this block here, so 6.2, which is the insufficient SIMD VGPRs, vector general purpose registers. The last example, it's gonna go over quickly, so hopefully it's not gonna be too quick, but basically we are exploring how data access patterns is important for performance, and this is actually probably one of the most important things, other obviously than the launch parameters. So basically, the problem implementation has a situation where the threads are striding. So they're accessing data that's not contiguous. And so they always have to make a jump in the way they access the data. And so they're not leveraging data locality. And the solution is the situation where we're actually leveraging that. So we're removing the striding so that the thread can access contiguous data. And then we're just going to run Rocprof-compute profile for both cases and check the results. So surprisingly, we got a slowdown, removing that. But we also got a lot better L1 cache hit. So now we are indeed making better use of the cache. So why are we getting the slowdown? Well, so in this example, there's also an atomic operation. So we need to check what happens with that, and maybe that's the bottleneck now. Now that we have optimized the data read processing, removing the striding. So see, filtering for block 17 to 11, that's the atomic latency. And for the solution, the atomic latency is higher than for the problem. So now, removing the striding, we're actually hitting another bottleneck, which is the atomics. And for that, what we're doing now is we are using a shuffle reduction to reduce the atomic contention. But still, that issue with the performance hasn't gone away. So it's still slower. So the solution for that was actually to basically use a bigger size for the problem. And this is kind of what I was thinking about the other day when people asked me about OpenMP versus HIP. Why was OpenMP faster? And I was thinking about problem size because at times, like in this case, if the problem size is too small, then you may get some misleading leads in your optimization quest. And after increasing the problem size, then we actually do see that we got the speed up that we were expecting. The performance for L1 is similar to the small problem, and the L2 hit rate is reduced. Yeah, so a couple of tips before finalizing this presentation. You can filter by kernel name. So if you already know that you're interested in a certain kernel, you can filter that with the -K. If you include the quotes, then you'll be able to include spaces in the kernel names. And then you can also use a subset of the metrics that Rocprof-compute will give you, basically by doing what I showed you right now. So with the -- blocks, that will show you only what you're interested in. Yeah, so we talked about the main features of Rocprof-compute, going from the roofline to the profile to the analysis tools. And in particular, we made heavy use of the Rocprof-compute analyze tool where we compared head to different implementations of a certain kernel to quantify what those changes produced in terms of performance. We've got our examples, and there's actually examples for OpenMP as well, if you're interested. And that's it. Thank you for your attention.
We have any questions on Rocprof-compute? It's probably the most valuable tool because if you got one kernel that is slowing down the code, you can often get some tremendous speedups by looking at how to optimize it. Okay, do we want to take time to do the exercises, or are you or not doing exercises? These are sometimes the most valuable exercises to do with the tools because it's difficult to figure out all the details with tools.
Yeah, the tools are always a lot to take in, so no problem if there's not questions right away. Takes a little bit of experimenting. But actually, since I have you all here, let me share in the chat this link, which I think is very, very helpful. And in a way, it's a little hidden. I actually found out about it kind of randomly. It just popped up on a Teams internal chat. So let me just point you to this public link here. So I posted it in the chat. I'll grab the screen real quick. So you may be wondering the meaning of what you see in that Rocprof-compute output. So for instance, if you're seeing my screen, you see here, there's this insufficient CULDS, and you're thinking, well, okay, what does that mean exactly? And then I included this screenshot here that's basically defining exactly what that means. So these definitions are at that link that I sent you, and you can select your specific architecture and basically navigate these files according to the block name. So here, see that insufficient CULDS sits in workgroup manager. So you go here, find the workgroup manager, and you can look for insufficient CULDS, and there's over here your definition. So I think this is very helpful to have handy because it tells you exactly what you're looking at, and maybe, knowing exactly what there's available, then you can tailor better what you're looking for. So there was another metric later on here that was called, well, we can look at the atomic latency, for instance. That's in the L2 cache. And we find exactly what it's, we find exactly the definition. The time average number of cycles atomic requests spent in Infinity Fabric before a completion acknowledgement or data was returned to the L2. So yeah, I think it's helpful to have this information. I posted that in the chat. Hopefully you got it. Oh, there's a question. Thank you. Which metrics should be checked to detect first touch penalty on MI300A? That's a good question. Maybe Bob knows, but I think that the first thing that you notice is that the performance is suspiciously slow. But yeah, if you want to measure that, I'll have to think about it.
It should show up in the latency, I think. The latency chart.
Let's go take a look. Yeah. Let's see if we can actually answer that question live. So the latency is, sorry, let's see. I think it's the memory. Hold on, sorry, I'm looking at the block. Well, maybe, let's see. Yeah, I don't know exactly. I'm gonna have to look it up and let you know. Because I mean, you can measure the like LDS latency, for instance. I don't know which one would be the number one marker to check. Yeah, good question. I'll ask.
Okay, should we move on, Giacomo? I'm not coming up with any direct answers. It's one of the problems of looking through the tables is trying to figure out what metrics are important. We should see lower bandwidth, see some memory stalls, but I'm not sure what line we see that on.
Yeah, I did a quick search and I couldn't find anything definite either specific to a 300A, but I asked our profiling experts, so hopefully we'll get an answer tomorrow, whatever tomorrow means at this point. Oh yeah, no problem, no problem. Okay, so I think the next presentation is the community tools, right? Let me go ahead and fire that up.